Hi, this is Shri, and I will be explaining de Moivre's theorem. So I know that complex numbers has been a pretty difficult subject in the past for a lot of students, so let's hope that this makes it slightly easier. So before we go into de Moivre's theorem, we need to explain, or we need to go over all the forms of a complex number. First, let's look at normal Cartesian form, which is z is equal to a plus b I. A is like the real part. It's along the x-axis and or the real number axis, and bi is the imaginary part, with b being like the coefficient for like the imaginary axis, right? So this gives both parts of the imaginary number or the complex number, and which is like denoted by z. Um, this is called the Cartesian form. Another thing, or like another form that we've also learned that is very, very useful is called polar form. Now, the way polar form is formed is by finding something called the modulus and the argument. So that will be explained in a bit. So first, modulus. Modulus is basically the distance between a point like on the imaginary plane and the origin. So let's just draw a really quick plane here, right? One, two, three, one, two. Sorry, I didn't have graphs pre-made, so bear with me here. So let's say you have a point at, I don't know, two plus two I, right? So this is two plus two I. The modulus is basically the distance between this center point, this origin, and this point. And I think all of you have done the distance formula before, and that's exactly what you have to do here. The modulus is found by, or it's denoted first by r, and it's found by the square root of the x squared. In this case, that's like a squared, because this is a and this is b. So a is equal to 2, b is equal to 2. So it's just a squared plus b squared. That gives you, square root of that gives you r, which is this modulus. Next, the argument. Argument is basically the angle between this r, this line right here, and the x-axis, the positive x-axis. So this axis right here. That means the angle that is formed in this case will be this angle right here between r and the x-axis, and we'll just label that theta. So basically, that is the argument right there, that theta. So we can denote the argument in two ways. We can just call it theta, or we can call it arg of z. Z being the complex number. So arg of z would give you the argument of the complex number z. And it's found using trigonometry. I know a lot of you are scared of trigonometry especially when it comes to complex numbers, but trust me, it's not that bad. So we know that this distance right here is b. Let's erase this for a second here to make it visible. So this number is b and this number is a. So in order to find theta, if you remember your unit circles and all that, is basically, or before we go into that, let's look at the relationship between a and b. The angle can be just written as the inverse tan of b over a, because tan of theta would be b over a. So let's say tan of theta is equal to b over a. So the inverse tan of that, to find theta, would be inverse tan, or arctan, whatever, of b over a. It's pretty simple, right? So now that, in this case, let's evaluate the argument, right? So, or find the argument. So arg of z is equal to tan, or the inverse tan of b over a, which is 2 over 2 in this case. So 2 over 2, which is just 1, is equal to, and the inverse tan of 1 is 45 degrees, or pi over 2. Or sorry, pi over 4. So that is the argument in this case. Now, to go from having an argument and a modulus to having a complex number in polar form, it's done with a little more trick. But again, it's not bad. So first, how can we describe A in the Cartesian form? A with respect to the argument and the modulus. Well, since we already know that A is like the bottom leg of this triangle that we constructed on this graph right here, so then we can just say that A is equal to R multiplied by cosine of theta, or cosine of the argument. Meaning, basically, cosine theta is, or let's just write it over here, cosine theta is equal to A divided by R, right? Because that's how trig works, I guess. It's adjacent over hypotenuse. So if you multiply cosine theta by R, you also multiply this by R. The other side, R's cancel out, and you're left with A. So A is equal to R cosine theta. B is the same, actually. B is equal to R multiplied by sine theta, because sine theta is equal to B over R, or, opposite over hypotenuse. So if you multiply both sides by R, cancel out the R's, you're left with B is equal to R sine theta. So let's look at this this whole form, the Cartesian form again. If we wanted to rewrite that in a polar coordinate form, then you say z is equal to A, or you just substitute the stuff in. So R cosine theta, let's just write A underneath it, you have to remember, plus I times B. B in this case is R sine theta, right? So I times R sine theta. Interestingly enough, both R cosine theta and I times R sine theta have R in common, so you can take that out. Z is equal to R times cosine theta plus I sine theta. And that is polar form. So now let's write the complex number that we found here. So 2 plus 2i, for which we found the argument and the modulus, which this is the argument. And, oh yeah, we forgot to find the modulus. The modulus of z, or let's just write r, is equal to the square root of 2 squared plus 2 squared. If anyone remembers their numbers correctly, that would just be a square root of 8, because 4 plus 4 is equal to this 2 times the square root of 2, 2 root 2. So this is the r, or the modulus, and we know the argument, which is pi over 4. We just substitute those in. Z is equal to 2 root 2 times cosine of pi over 4 plus I times sine of pi over 4. And mathematicians, being the lazy people that we are, have invented a shorthand of polar form, which is z is equal to r times cis theta. Basically, it means z is equal to r times cosine theta to I sine theta. It's weird, but it's just the shorthand version of it instead of having to write cosine theta plus I sine theta every single time. So z is equal to r cis theta. That is where r cis comes from. If you guys saw that phrase in your textbook or remember it from class, that is where that comes from. So those are Cartesian form and polar form. Let's look at multiplying polar form points. So let's just open a new page. That one invisible. So let's go over polar form again. It's just z is equal to r times cosine theta plus I sine theta, right? So let's look at multiplying two different polar form coordinates, or two polar coordinates in complex numbers. So let's write, instead of theta, let's just make it theta 1 for r1 and theta 1. This is talking about our first polar coordinate, right? Just with the argument of the first argument, first part, modulus. That's all we're just saying. And let's just say this is z1. And then z2 is equal to r2 cosine theta 2 plus sine theta 2, or sub 2, whatever you want. So if we were to multiply these, multiplying them would just be, well, I guess you just take these out. So it's just I'm gonna write this as r cis because that's easier. R1 cis cis theta 1 multiplied by R2 cis theta 2. You're just multiplying these 2 points. And here's what you get. So you just, I guess, you just multiply them together, right? So R1, R2, cis theta 1 times cis theta 2. And we can't leave it like this, obviously. So let's expand this part. Let's take R1 and R2 out. So R1, R2 in parentheses. We're basically multiplying this times this, which if we multiply them right, let's just do that right now. So cosine theta 1 times cosine theta 2 plus, sorry, I actually forgot the I up here in the Z2. Then you just get, and then you keep multiplying, right? So I cosine theta 2 sine theta 1 plus, keep multiplying, I cosine theta 1 plus, oh sorry, not plus, sine theta 2 plus, and then finally, I times sine theta 1 times sine theta 2. If you guys remember, I squared is just -1, so technically that's not even a plus sign, that's a minus sign. And it's just minus sine theta 1 sine theta 2. That's it. That's how you expand that. Wait, actually, let me just make this, oh, sorry. Let's just make this a little prettier and make that, let's just rotate that because that's hurting my eyes when I look at it because it's all wonky. and like put that right there. That's better. So now let's simplify this, shall we? All right. So let's look at the one thing that we first notice, right? Um, two of these terms, this one and this one, have I in them, like or I multiplied to them. So they're both like imaginary parts. And then these two parts do not, so we can call them the real part. So let's combine them together in that way, and we'll see that you can find two different trig identities. First, cosine of a plus b is equal to cosine a times cosine b minus sine a times sine b. The other one is sine of a plus b is equal to cosine of, let's just say, let's start off with cosine a though. Yeah, cosine a sine b plus cosine b sine a. And in this case, the imaginary parts fit the sine a plus sine of a plus b, and the real parts fit cosine a plus b. So we can rewrite that as such. In this case, we're just saying that a is equal to theta 1, b is equal to theta 2. By the way, these trig identities are very useful, so please do remember them for future reference and your IB exams and whatever. They're pretty important and very, very useful. All right, so let's just rewrite these. Modulus goes over here, R1, R2, multiplied by cosine of theta 1 plus theta 2 plus I, remember I is very important, sine of theta 1 plus theta 2. This is how you multiply two different complex numbers, at least in polar form. Let's just write z1, z2 here, so we remember that. So this is how you multiply them. You can do the same with exponents as well, which we'll do that right now. It's basically the same thing. It's just that instead of having an R1 and R2 and theta 1 and theta 2, you have the same numbers. So in that case, instead of having R1 times R2 times cosine theta 1 plus theta 2 plus I times sine theta 1 plus theta 2, if you just make all the angles the same and the arguments the same, and let's just look at r cis theta squared. Z squared is equal to this, right? So we're just looking at like how to do this, and it's basically what we just did. Same modulus, same argument. So instead of all of these different terms and everything, you can just write it as z squared is equal to r squared, or modulus squared, multiplied by cosine of 2 theta plus I sine of 2 theta. It's that simple, because you already found what you did before with multiplying polar forms. You just use that and find how to do exponents with these. Now this is where de Moivre's theorem comes in to play. Let's just open the page. De Moivre's theorem says that z to the n is equal to, oh, I apologize, is equal to r to the n multiplied by cosine of n theta plus I times sine of n theta. Pretty simple, isn't it? So this, like, let's say if you have the exponent of 3, so z cubed is equal to r cubed times, I'm just going to write cis this time because it's simpler. So cis of n, or 3 theta. And this makes it a lot simpler to find the like exponents of a complex number and stuff. So one thing that is very important to remember about polar form is that a single number can be written in multiple different ways. One complex number. Let's make this a little bit easier for ourselves to understand. Let's just look at z is equal to 1. It's just 1. Which is also z is equal to 1 plus 0, sorry, 1 plus 0 I. Oh my god. I. Meaning that there is no imaginary part and there's only a real part. So the ways that this can be written in polar form is numerous, I guess. So let's just get this to polar form first. If you remember, we have to first find the modulus and the argument. Luckily for us, in this case, modulus is just 1 because r is equal to square root of 1 squared plus 0 squared, which is just 1. Argument, z is equal to arctan, or tan, the inverse tan of b over a, which is 0 over 1, which is sorry, I had to do something, which is 0. So so in this case, like the polar form would be written as 1 times cis of 0. It's pretty simple that way. But what numbers, like how many different ways can theta, or tan of theta equal um, 0, sorry. Well, you can have tan of 0, right? Which tan of 0 just gets you 0. Or you can have or you can have 2 pi, because it's just like full rotation. So if you have a plane, starts over here, which is 0, then you have a full rotation, then you go back to the same point with 2 pi. You can have 4 pi, which is just doing the same thing, but another time. 6 pi, and it goes on, right? And it gives you the same result each time because that's luckily how polar form works and trig works. Meaning that a complex number such as 1, which is just a regular just real number, can be written in multiple forms like 1 cis 0, or 1 cis 2, 2 pi, and then it can 1 cis 4 pi, and it goes on like that. And basically, it's we can simplify this as 1 cis of 2 pi, or rather, like, it's just you can just write it as n minus 1 times 2 pi. This gives you basically every single way that you can write 1 as a complex number in polar form. And there will always be like n solutions or n different ways that you can write it, right? So this gives us something like really interesting because we can find something called roots of unity. So roots of unity are basically the number of ways that a complex number raised to an exponent can equal another number. So you know how like 1 can be written as 1 squared or negative 1 squared? It's kind of like that. So let's say you have a complex number, z, to the power of n, right? So we raise z to the nth power. Let's say how many different ways can that equal 1? So since z is a complex number, let's just rewrite this. Z is equal to r cis theta. R cis theta. And we raised it to the nth power is equal to, and let's just rewrite 1 as a complex number as well. And we just did it earlier. So it's 1 cis 0, basically. Or let's say, yeah, 0. So if we raised, I don't know. If we raised r cis theta to the power of n, because we looked at the Moivre's theorem, the way we write that is r to the n times cis of n theta is equal to 1 cis 0, I guess. So since both sides are on like in the same form, we can do something really neat because the I guess it's like parallel. So we just say r to the n is equal to 1, and then cis of n theta is equal to cis 0, or n theta gives you the same result as 0. By the way, because we looked at how technically it's not just 0, it can also just be 2 pi, 4 pi, 6 pi, and on. These can also be substituted into this equation to find more solutions. So r to r to the n is equal to 1, and you kind of just like solve it because like if you say that if you say that the exponent is a specific number, then it like matters how you solve it. But like since in this case we just chose the other complex number to just be 1, r to the power of like anything is still just gonna be 1. Or sorry, if n is any integer or any number really, and it's the entire thing is equal to 1, so then r is just equal to 1 as well. R is equal to 1. All right, so next one. N theta is equal to 0 or 2 pi or 4 pi or 6 pi. You just say theta is equal to 0 over n, 2 pi over n, 4 pi over n, and it goes on. So the objective of this was to find the complex number. Let's say that let's go back to here. What we were trying to do is, let's say we knew what the exponent was, we knew what this was, n, right here, and we knew that it was all equal to 1 in this case. We were trying to find this complex number, which we didn't know, so we substituted r cis theta into it. But now that we've solved r, which is the modulus, and theta, which can be any of these, it gives me every single complex number that can be raised to the power of n and equal 1. So we have 1 cis 0, 1 cis 2 pi over n, 1 cis 4 pi over n, etc. And if we say we raised z to the power of 4, and we tried to find that equal to 1, so z to the power of 4 is equal to 1, then this equation would have 4 solutions. So since we just found the series of solutions earlier right here, so we can just say the solutions are, or what is z, like the complex number z. If we're trying to find z, it would be 1 cis 0, 1 cis 2 pi over 2 pi over 4. So oh my god. Okay. 2 pi over 4, 1 cis 4 pi over 4, and it goes on. And we can obviously simplify these because this just becomes pi over 2, this one, and this just becomes pi. So that gives us each solution. And there's something even more interesting is that if you have oh my god, if you have a complex number plane and you graphed each of these numbers, so let's just say that this right here is 1 cis 0. 1 cis 0. I forgot that was 0 and not theta. Next one, 1 cis pi. So you have a modulus of 1, or sorry, half 1 over 2 pi. So modulus of 1, and you, so like we can just draw a circle at 1. Sorry, this is a very bad circle. I'm doing this on like an uneven surface, kind of. You know what? Let's just make it a better circle. I think I love having an iPad, by the way. This thing allows me a lot of freedom to mess up and still do stuff. Alright. So, that's good enough. So, that's the circle, right? So, we need 1 cis 0, 1 cis pi over 2. So, that's like right up here. So, these are our 2 points. 1 cis pi, 4 pi over 4 is just pi. So we have one argument and then pi radians, so it's over here. And then if we continue this, the next term would have been 1 cis 6 pi over 4, which is just 1 cis 3 pi over 2, which is right over here. And there we have our 4 solutions. And the cool thing about it is that the angle between them is always the same. You know, like this is always going to be theta, right? Or let's just write that over here. It's just 1 point that is rotated by theta degrees every single time. Not only that, this also forms a regular polygon. In this case, it forms a square. Let's say you have a complex number raised to the power of 6. Z to the power of 6 is equal to 1. I'm using 1 because it's a very simple example, but obviously in other questions, like on the IB exam, you're going to be asked more difficult questions, with 1 being some random complex number that is much more difficult, and I don't want to deal with that right now. And it's probably much easier to understand with 1, isn't it? So r cis theta raised to the 6th power is equal to 1 cis, I'm just going to put it as theta 1 and theta 2 because I don't want to have to say substitute it for 0, 2 pi, whatever, every single time, right? It's easier this way. So r to the sixth cis of 6 theta is theta 1 is equal to 1 cis theta 2. And now we just say r to the 6 is equal to 1, meaning that r is also equal to 1, and that's our modulus. And then our argument is 6 theta is equal to 6 theta 1 is equal to theta 2. So theta 1 is equal to theta 2 over 6. And because theta 2 can be any of those angles that were mentioned before, the angle in this case could just be 0 over 6 or 2 pi over 6, 4 pi over 6, 6 pi over 6, 8 pi over 6, and 10 pi over 6. And this gives you every solution for z to the 6th is equal to 1. These are all of the arguments right here, and this is the modulus. So let's graph them. So you have complex number plane, and let's say, let's make a circle first, Oh, that's a bad circle. It's fine, I can edit it. Let's just make it centered, right there, something like that. Oh, all right, there. Let's graph the first one. 1 cis, or let's just write cis because 1 is implied, because in this case modulus is 1. So cis of 0, so it's just 1. So this distance right here is 1, by the way. Cis of 0, cis of 2 pi over 6 is just pi over 3. Pi over 3, if you guys remember, is basically 60 degrees, so it's going to be something like here. Let's make that a little better. Right here. Cis of 4 pi over 6, which is 2 pi over 3, which is right about here, I think. Yeah, something like that. So then cis of 6 pi over 6, which is pi over just pi, and pi over is over here. Then cis of 8 pi over 6, which is 4 pi over 3. Is right there. Yeah, something like that. And then finally, cis of 10 pi over 6, which is 5 pi over 3. And that is right here. Voila! All of our solutions on the complex number plane, each one rotated by a specific angle. And it forms a regular hexagon, which I think is pretty cool. Forms a regular hexagon. Each angle is just theta times some number, so just theta, and then 2 theta, and then 3, 4, 5, 6, and it just goes on like that, right? So if you add it up, but each angle is theta. So yeah, that's how you do roots of unity, or find roots of unity for a number or a complex number that is raised to an exponent and is equal to another complex number. So that should give you, or at least all of this should give you a basic idea of complex numbers in polar form and how to use de Moivre's theorem. I hope you have a great day. Thank you for listening to me for 40 minutes, or I guess 20 minutes if you put it on 2-speed, which is what I normally do, which I highly advise, by the way, unless you need to pay attention very closely. to like pick something up. But other than that, uh, thanks for watching, and I'll see you on the next one.